Today I'm going to introduce the math about brachistochrome curve. To solve this brachistochrome curve problem, there is about 3 solutions: Johann-Bernoulli solutions, Jacob-Bernoulli solution, and Newton's solution, respectively. However, we will just choose the first solution, which are Johann-Bernoulli solution, which has 2 ways to solve it. First of all, for the direct method of Johann-Bernoulli solution, there are 2 solutions: an analytic solution and synthetic solution. And then is the synthetic solution. He then proceeds that he called this synthetic solution, which was a classical geometrical proof that there is only a single curve that a body can slide down in the minimum time, and that curve is the cycloid. Assume AM and B is the part of a cycloid joining A to B, which the body slides down in the minimum time. Let ICCJ be part of a different curve joining A to B, which can be closer to AL than AM and B. If the arc MM subtends the angle MKM as its center of curvature K, that the arc on IJ that subtends the same angle would be CC. The circular arc through C with center K is CE. Point D on AL is vertically above M. Join K to D, and point H is where CG intersects KD, extended if necessary. That tau and T be the times that the body takes to fall among MM and C respectively. Like T is perspective, like the sentence here. Extend CG to point F where CF equals to CH squared divided by MD, and since MM divided by CE equals to MD divided by CH, it follows that tau over T equals to MM over CE times CG over MD to the 1 over 2, and equals to CG over CF to the 1 over 2. Since Mn equals to Nk for the cycloid, then GH equals to MD times HD divided by dk, and equals to MD times Cm divided by Mk, while CH equals to MD times CK divided by Mk, and equal to MD times Mk plus Cm divided by Mk, and CG equals to CH plus GH, and equals to MD times Mk plus 2Cm divided by Mk. If CE is closer to K than MM, then CH equals to MD times Mk minus Cm over Mk, and CG equals to CH minus GH equals to MD times Mk minus 2Cm divided by Mk. In either case, CF equals to CH squared divided by MD and larger than CG, and it follows that tau smaller than T. If the arc CC is subtended by the angle infinitesimal angle MKM on IJ is not circular, it must be greater than CE. Since CEC becomes a right triangle in the limit as the angle MKM approaches 0. Note, Bernoulli proves that CF larger than CG by a small, similar but different argument. From this, he concludes that a body traverses the cycloid A and B is less time than any other curve ACB. Okay, last but not least is brachistochrome problems, curve problem. Like in figure 1 shows George's diagram, expect the additional line IF is absent from it, and Z, the start point, has been added. The curve CVA is a cycloid and CHV is its generated circle. Since it appears that this body is moving upwards from E to E, it must be assumed that a small body is released from Z and slides along the curve to A without friction. Under the action of gravity, consider a small arc EE which the body is ascending. Assume that it traverses the straight line EL to point L, horizontally displaced from E by a small distance, O, instead of the arc EE. Note that EL is not the tangent at E, and that O will be negative when L is between B and E. Draw the line through E parallel to CH, cutting EL at N. From a property of the cycloid, En is the normal to the tangent at E, and similarly, the tangent at E is parallel to VH. Since the displacement EL is small, it differs little in direction from the tangent at E, so that the angle ENL is close to the right angle. In the limit as the arc EE approaches 0, EL becomes parallel to VH, provided O is small compared to EE, making the triangles ENL and CHV similar. Also, an approaches that the length of chord EE and the increase in length EL minus EE equals to NL equals to O times CH divided by CV, ignoring terms of O squared and higher, which represent the error due to approximation that EL and VH are parallel. The speed along EE and or EL can be taken as that at E proportional to square root CB, which is as CH, since CH equals to square root CB times CV. Well, this appears to be all that geography's note contains. Let T be the additional time to reach L, we got this sentence. Therefore, the increase in time to traverse a small arc displacement at one endpoint depends only on the displacement at the endpoint and is independent of the position of the arc. However, by Newton's method, this is just the condition required for the curve to be traversed in the minimum time possible. Therefore, he concludes that the minimum curve must be the cycloid. He argues as follows: assuming that now that figure 1 is the minimum curve not yet determined, with the vertical axis CV and the circle CHV removed, and figure 2 shows part of the curve between the infinitesimal arc EE and the further infinitesimal arc EF, a finite distance along the curve. The extra time t to traverse EL is NL divided by the speed at E, ignoring terms into O squared or higher. So we got this sentence. At L, the particle continues along the path LM parallel to the original EF to some arbitrary point M, as it has the same speed at L as at E. The time to traverse LM is the same as it would have been along the original curve EF. At M, it returns to the original path at point F. By the same reasoning, the reduction in time t to reach F from M rather than from F is this sentence. The difference, t minus t, is the extra time it takes along the path ELMF compared to the original EEFF, like this sentence. And because EFF is the minimum curve, t minus t must be greater than 0, whether O is positive or negative. It follows that the coefficient of O in 1 must be 0. d over this sentence, okay, in this limit as E and FF approach 0, note that since EEFF is the minimum curve, it has to be assumed that a coefficient of O squared is greater than 0. Clearly, that has to be two equal and opposite displacement, or the body would not return to the endpoint A of the curve. If E is fixed, and if F is considered a variable point higher up the curve, then for all such points Fg over Ff square root Ci is a constant. By keeping F fixed and making E variable, it's clear that d over E square root Cb is also constant. But since points E and F are arbitrary, that's the equation which has shown above to be constant, and the brachistostroom is the cycloid. Well, for the cycloid, for the cycloid, d over EE equals BH, B over VH, and equals CH over CV, so that d over EE square root CB equals CH over CV square root CB, which was shown above to be constant, and the brachistostroom is the cycloid. Newton gives no indication of how he discovered that the cycloid satisfies this last relation. It may have been by trial and error, or he may have recognized immediately that it implied this curve was a cycloid. Okay, and that's the math part, and I'm telling the joke that I am the joke, and thank you for listening. That analytic solution. Okay, a body is regarded as sliding along any small circular arc CE between the radii KC and KE with century K fixed. The first stage of the proof involves finding a particular circular arc, MM, which the body traverses in the minimum time. The line KNC intersects AL at N, and line KN intersects it at small capital N, and they make a small angle CKE at K. Let NK equals to A and define a variable point C on Kn extended. Of all the possible circular arcs CE, it is required to find the arc MM, which requires the minimum time to slide between the two radii, Km and Km. To find MM, Bernoulli argues as follows. Let Mn equal to x, he defines M, so that Md equals to Mx, and N is so that Mm equals to Nx plus Na, and notes that x is the only variable and that M is finite and N is infinitely small. The small time to travel along the arc MM is mm divided by md to the 1 over 2 equals to n times x plus a divided by mx to the 1 over 2, which has to be a minimum. He does not explain that because mm is so small, the speed along it can be assumed to be the speed at m, which is as the square root of md. The vertical distance of m, though, below the horizontal line AL, it follows that when differentiated, this must give x plus a times dx divided by 2x to the 3 over 2 equals to 0, so that x equals to a. This condition defines the curve that the body slides along in the shortest time possible for each point M on the curve. The radius of curvature mk is cut in two equal parts by its axis AL. This property, which Bernoulli says had been known for a long time, is unique to the cycloid. Finally, he considers the more general case, where the speed is an arbitrary function x of x, so the time to be minimized is x plus a divided by x. The minimum condition that becomes x equals to x plus a times dx divided by the small capital X, which he writes as x equals to x plus a dx delta x, and which gives mn as a function of nk. From this, the equation of the curve could be obtained from the integral calculus, though he doesn't demonstrate this.